Let me just start by admitting that this man's last name is probably not pronounced Bernoulli, but that's the way physicists usually pronounce it. So, the Bernoulli equation, let's figure out where it comes from. In your lecture notes, I kind of just presented as a result without much justification. So imagine that we're given a reversible flow, and it can be something like this, where there's an obstacle, and you have stuff flowing around it. So what I've drawn is a streamline, which tells you the path if you have a fluid element that starts at location 1 and flows around the obstacle in a steady reversible state. Then it gets to location 2, and it has to follow this path and experience a change in its properties, potentially, that we'll be able to describe using the Bernoulli equation. So what ingredients do we need to use to derive the Bernoulli equation? Well, the first is entropy balance. So in this case, I'm providing entropy balance for a steady state, meaning that the left-hand side is 0, and that's just q dot t plus m dot s1 minus s2 is 0. Remember, the subscripts there will refer to the locations 1 and 2. We're going to use one of the Tds equations, so you're very familiar with these by now, and we're going to use conservation of energy for an open system. Okay, so I'll put that in its full glory up there. How do we combine these? Let's start with entropy balance. So 0 equals q dot over t plus m dot s1 minus s2. And we can rearrange, just bring q dot over t to the other side, so that'll change the sign on s1 minus s2 to s2 minus s1. That's fine. Let's multiply both sides by t and divide both sides by m dot to rearrange in this manner. Why would we do that? Well, now I have a right-hand side of this expression that we could rewrite as the integral of TdS. And of course, the reason to do that would be that we want to use the TdS equation. So let's rewrite that. Now if we have the integral of TdS, of course, we can substitute in our expression for TdS there. So let's do that, and we get the q dot over m dot equals the integral of the quantity dH minus little v dP. And the v there, of course, is specific volume. Okay, we'll use that in a minute. We'll move that up. Let's separate that integral into two separate integrals, 1 over dH and 1 over v dP. And of course, we can solve the integral over dH, it's just going to be h2 minus h1. We'll leave the integral of v dP as it is. So now we need to evaluate the difference in specific enthalpy. So for a steady state, one inlet, one exit, we can use energy conservation to say that, well, the left-hand side of the energy conservation law has to be 0, right? Because it's steady state. One inlet, one exit means we just have one m dot, which is great. So we can rewrite that down here. All we have is the left hand equal to 0. And we're actually going to keep all of these terms except for the work. There's no evidence that any work is being done in this system. I didn't say anything about work. Let's go ahead and set that to 0. So the expression down there reduces slightly, but we still have a lot of terms. Now what I've done is solve for q dot over m dot. So I had to change the ordering of all the subscripts, right? Now we have h2 minus h1, v2 squared minus v1 squared, and z2 minus z1. We want to make sure to track the signs correctly so we don't get something nonsensical. Okay, let's move that up a little bit. Well, the nice thing is this combination up here, q dot over m dot equals h2 minus h1, also occurs in our energy conservation expression. So that must mean, if those two are equal, that the remainders of each equation are equal, right? So that tells us that this bit down here is equal to that integral up there with the correct sign. So let's equate those two things I have circled right now. All right, we do that, and we get that 1/2 times the difference in squared velocities plus g times the difference in heights must equal negative integral of v dP. Usually this is rearranged so that one side of the equation is 0, and we get the final form of the Bernoulli equation that 0 equals the integral of v dP times the difference in square velocities divided by 2 plus g times the difference in elevation. Okay, so when is the Bernoulli equation useful? Well, remember, it has to be a reversible flow. So if you have a bunch of irreversibilities in your flow, you can't do it if there are a bunch of processes occurring generating irreversibilities. If sigma dot is not equal to 0, it doesn't work. You also need this to be a steady flow. So that means that the properties at location 1 always have to be the same. They can't be changing in time. Same at location 2. Now, when a fluid element moves from location 1 to location 2, of course its properties can change, but that's different. The properties, generally speaking, at location 1 always have to be the same in time. The nice thing is, when correctly applied, though, this gives you a lot of freedom to actually change properties along a streamline, right? So you can have a fluid element experience changes in specific volume, pressure, velocity, and elevation, and the Bernoulli equation tells you how all of those changes would be related.